Hello there, this is Mr. Roche and his sidekick Wilson, and welcome to Mr. Roche's Flip Class Math 10 no frills, no thrills, low budget, low tech videos. That's what I'm trying to say. This video is called Systems of Linear Equations Part 1, and it's about solving systems graphically. I'll describe what we're going to be doing as soon as I put Wilson down. Here you go, Wilson. Okay, in this particular video, I'll be defining what a system is. We'll be talking about the number of solutions to a system of linear equations. We'll be solving a system graphically, and finally verifying a solution to a system. So here we go. First of all, defining a system. A system is multiple relations, usually in some sort of equation form, written in the same two variables. That's the key, it's got to be the same two variables, otherwise it's not a system, we can't solve it. So for example, here are two relations. One that happens to be in slope y-intercept form and the other one's in standard form. But as you can see, they have the same variables. So therefore it's a system. It is possible to have more than two, but usually we're talking about two different relations. Here's another example of a system. They have the same variables, p and q. So secondly, the number of solutions to a system of linear equations. Okay, first of all, solution is the ordered pairs whose coordinates satisfy each relation. It's important to realize that when we have a relation, say on a graph, any point along that graph will satisfy that relation. In other words, if we find an ordered pair 5, 8, and put 5 in for the x and 8 in for the y in that equation will work out mathematically. Okay, and that's so there's an infinite number of solutions on any linear graph or any linear equation. However, the solution for a system has to work in both of the relations. Okay, here we go. It is possible to have 0 solutions. It is possible to have one solution. And it's possible to have infinite solutions. And remember, we're only talking about linear equations here. It does make a difference if we're talking about nonlinear relations like we would have in grade 11 or 12. Okay, examples of each of that will be coming up in a minute. Okay, so solving a system graphically. Here's an example. This is the same one that I had up here a second ago. This is slope y-intercept form and standard form. So we're going to graph those on here and try and determine this the solution to that system. Okay, so here are the steps I'm going to follow. I'm going to graph each relation. Okay. So this one here, if I graph it, I know that the y-intercept is -7. So 1, 2, 3, 4, 5, 6, 7, right there. And I know that the slope is 3, so I'm going to go over 1, up 1, 2, 3. In other words, the run is 1 and the rise is 3. A run of 1, rise of 3. A run of 1, rise of 3. I can do this all day long. So if I graph this, or join this up with a line, there it is. And again, any point along that line should satisfy that particular relation. Okay, so the point 1, 2, 3, 4, 1, 2, 3, 4, 5. So the point 4, 5 should fit work in here. Let's see. 3 times 4 is 12, minus 7 is 5. Yeah, it works. Okay. Now let's graph the other one. To do that, I'm going to find the x and y intercept. That's probably the easiest. So I'm going to make the y equal to 0. If I make that y equal to 0, of course that term will become 0. So x is going to be 6 if I divide both sides by 2. So 1, 2, 3, 4, 5, 6, right there. And now I'm going to find the y-intercept, so I'll make x equal to 0. So that will become 0. And y has to be 4 if I divide each side by 3. So 1, 2, 3, 4. There we go. And I'm going to join those up. Okay. So now I have my two graphs. This one here, any point along there would of course satisfy the second relation. But, of course, there's only one point that will satisfy both relations, and that's that one right there. And the coordinates of that are 1, 2, 3, 1, 2. So 3, 2 are the coordinates of the solution to that particular system. Okay. Now I'm going to verify that. So we just found that the solution to this system was 3, 2. Okay, the way that I'm going to check that is to put these points into this equation, put these points into this equation, and make sure it works. So let's try into this equation. The y is 2 equals 3 times x is 3 minus 7. 2 equals 9 minus 7. 2 equals 2. So my left side equals my right side, so we know it works in that particular relation. Let's try this one. 2 times 3 plus 3 times 2 equals 12. That's 6 plus 6 equals 12. 12 equals 12. Left side equals right side, so I know it works in there. And of all the different ordered pairs in the whole universe, only that one would satisfy both. That is the solution to that system. So how could it possibly be different than just one solution? Well, here I just made up a few sketches for examples. As mentioned previously, a system can have one solution, like the one we just did, and that solution would be where they intersect right there. Okay? It could have no solutions. Well, that would be the case when we have parallel lines. You'll see, with parallel lines, the slope is the same, the y-intercept is different. Infinite solutions along here, infinite solutions along there, but not a single solution that would work for both, okay, because they never intersect or cross. And finally, we're going to have infinite solutions, and that's when we have collinear lines, or overlapping lines, if you wish. Those are equivalent relations. They might look different, they might be in different forms, or one might be a simplified version of the other, but when we graph them, it's one line on top of the other. So we would have an infinite number of solutions all the way along that line. And that's it. My next video will have to do with solving systems algebraically. One way is by substitution, other way is by elimination. And those are particularly useful when they intersect at a point that's doesn't have nice integral type coordinates. For example, if we start dealing with fractional coordinates and so forth, the graphing becomes a little more difficult to be accurate. Okay, that's it for now. Thank you for joining us.